Okay, welcome class. We're doing chapter 11 today, heat engines. Let's get into it. Okay, thermodynamics. Wow, that sounds important. It is. Thermodynamics is really important. One of the most important disciplines. Okay, what is a heat engine? Well, here's a typical engine that would be in a car, right? You got a fan, there's the air intake. This looks like an old carburetor engine, right? Now they're fuel injected. So, and here's the basic concept in engines that are in cars, right? You have a spark plug, you have a fuel and air mixture, you have combustion. The spark plug sparks, it ignites the fuel air mixture, you have combustion, so the heat increases. There you go, heat engines, right? So the heat increases. We learned from the last chapter that if you have an increase in heat, well, you're increasing pressure. So here you have a lot of heat, a lot of pressure. Now it does work, right? We know all about work. We've been studying work since very early on in the semester. So it pushes this piston up. Now in this cylinder, this is inside of an engine, in the engine block, in a car or a motorcycle, right? It will push this up and it's going to crank, right? You may have heard terms like a crankshaft, that sort of thing. So it turns up and it turns up and it turns this, and eventually it goes to the drive shaft and it turns the tires and your car goes, right? And then the next cycle it comes down, it pushes the exhaust gas out, right? And that's what comes out of your tailpipe, right? It goes through your muffler, comes out of your tailpipe, that's the exhaust. Then the whole cycle starts again, right? So it keeps doing that. Heat engine, a lot of heat, increases pressure, does work. Oh, and there's waste heat, right? The exhaust gas that comes out of your tailpipe is hot. It's not as hot as here though, but also you have a radiator in your car. That's for the waste heat, because a lot of this heat, it doesn't just go into work. It goes through the metal. You have a radiator. You have to keep your radiator fluid up, right? So there's a lot of the energy is wasted, is waste heat. That's a big concept in what we're going to be talking about. Oh, I should have just done this. It explains it all here. Oh, this is pretty much what I said. So yeah, it expands, it does work, and it transfers to the drive shaft and turns the wheels, right? So. Yeah, the wheels push against the road, right, and the car goes. So. Now, not all heat from burning fuel is converted to work done in a moving car. The exhaust gas, right, is warm, so there's heat. And then there's also heat just because of the radiator. So it's not completely efficient. If it was completely efficient, all of this heat would go to do work and you wouldn't have any waste heat. But there's no such thing as a purely efficient engine. There's always waste heat. It's just the way the universe works. And this is a diagram to show that. So you have this amount of heat to begin with. This would be the heat that's inside the cylinder, right? So part of that heat did work. It pushed the cylinder up, and then that turns the tires on the car. But then there's waste heat, right? So here it's like heat that's higher at a higher temperature. Here's heat at a colder temperature, so H and C. And then work is what we want. We want to get as much work as we can and have as little waste heat as we can. That's always the goal, make it more efficient. Some of the energy, mechanical work, waste heat. I should just do this instead of talking ahead of time. Yeah, and we have a nice little equation here. So, and we can see this from a diagram. So Q, right, here where you have the higher heat, it's equal to, well, you have some of it went into work, and some of it is waste heat, the colder. Yeah, I mean, it's still hot, but it's a lot colder than this, right? So you have waste heat that comes out. And if you add these two, that's what your original amount of heat that you put into the system. So efficiency, this is a pretty simple equation. So you have your work. Work is what you want, and you divide it by the total amount of heat that you put into the system, okay? So the more efficient an engine, and you want this as small as possible, you want this as big as possible. So an efficient engine, right? You divide the total amount that you put in. Okay, you divide work by the total amount that you put in, and that's your efficiency. Okay, and here's a nice little problem. A heat engine takes in 1,200 joules of heat from a high temperature heat source and does 400 joules of work. What is the efficiency of this engine? Okay, so this part is 1,200 joules. This part is 400 joules, so you simply divide, just like I showed before, 400 divided by 1,200. So this engine would be 0.33 or 33% efficiency in that engine. And then here, it's just this. So here you have QC, we have the total heat input. Well, you use 400 to do work, so there's 800 joules left as waste heat. Okay, Carnot. This is a French, so it's Carnot engine. He was a French person who came up with this. He was trying to figure out how efficient could you get, can an engine get, and what he determined is that you can never get there's always going to be waste heat. Therefore, there's no such thing as a 100% efficient engine. There's always going to be waste heat. All right, let's get on. Yeah, this is an example. Let's go to the efficiency. So this is the important equation that we want to know. So what you do is you take your highest temperature, and then you subtract the temperature of your waste heat divided by your highest temperature, and that gives you the efficiency. That gives you the efficiency of the system. And as you can see, the greater the temperature difference here, the more efficient the engine is going to be. Keep that in mind. That's why power plants, power plants where we get our electricity, they all eventually have steam generators. Even nuclear power plants. The nuclear doesn't convert directly to electricity. What they do is they just use it for heat, and they just turn turbines using steam. So a lot of people don't realize that. Yeah, so you want this to be a greater difference, and that's efficiency, Carnot efficiency. So it's this equation. And here we're just going to use that equation. Now notice that, so we're given that a steam turbine takes in steam at a temperature of 400 degrees C. Remember that water boils at 100 degrees C, so 400 is quite hot, and releases steam to the condenser at a temperature of 120. So when it's done doing work, 120, the steam is at 120 degrees C. So they want to know the Carnot efficiency. Now look here, you want to do your math in Kelvin, so you want to convert to Kelvin. Remember, you add 273 degrees. So you add 273 to 400, 673, you add 273, right? Then you just plug it into this equation. Notice where the parentheses are. Do this first, then divide it by that, right? Okay, so you can get 41%. So steam engines are typically more efficient than automobile engines. We're going to talk more about that in just a bit. And here's another example where we did a similar example in each cycle with the maximum amount of work. Right? This is similar to the example we did just earlier. Yeah, so here they're just saying you can't convert all the heat into work. We wish we could, but the universe doesn't work that way. There's always some heat loss, right? And here they're just giving some examples of, yeah. All right, let's move on. It's just restating what we said. Okay, so, you know, we talked about refrigerators in the last chapter. We you know, how does a refrigerator make things cold, right? Well, you expand a gas. When you expand a gas, the temperature goes down, right? So that's the basic fundamental principle. But we know that heat wants to flow from, you know, a place where there's more heat, where there's a higher temperature, to a place where there's less heat, lower temperature. That's the natural thing. So in order for a refrigerator to work, the only way it works is that the motor in the refrigerator, right, the compressor has to go and make the system work. So inside the refrigerator you have a colder temperature, right? And then in the back of the fridge there's always those coils. Those are warm, so it's getting rid of heat into the room, but you have to do work, right? That's why your refrigerator, that motor always comes on. Mine makes a lot of noise, right? It's kind of annoying. And so you have to put work into the system for your refrigerator to work. And they call that a heat pump, right? That's a heat pump. It's not the natural flow. The natural flow would only be down in this direction, but you can make this work. Refrigerators work, obviously, right? I can make ice in my refrigerator. You have to put work into the system in order for that to happen. So that's what that's saying. All right, and yeah. So work plus a lesser amount of heat will give you a greater amount of heat, but you have to supply work. So in no case does it ever happen by itself that way, right? And here you go, right? So in the back of the fridge, there's those coils back there. It's usually against the wall. Those are warm, so it's getting rid of your high temperature heat. It's just getting rid of it, dissipating it into the room. So. All right, let's move on with this. They're just talking about some examples, and I'm just going to use the refrigerator example. So that's good enough. All right, let's move on. Oh my God, let's keep going. Yeah, heat will not flow from a colder body to a hotter body unless some other process is also involved, right? That process is work, right? Work can be used to pump heat against its usual direction of flow. Okay, refrigerators. And then they're just giving more and more examples. So, okay, entropy. Entropy, you know, the state of the universe naturally becomes more and more disorganized. The natural state of things is to go from organization to less organization. Now you can have temporary situations where entropy is increased. For instance, babies are born, right? You just eat food, which is kind of chaos. You're breathing air. Well, babies are born, but you're putting energy into the system. So the natural order is for molecules and gases and everything in the world to just become more and more disorganized. But you can, if you put energy into the system, then you can organize stuff. But entropy only decreases if you put energy into the system. You do work for that to happen. So the entire universe, entropy is increasing, meaning it's becoming more and more disordered, right? And they go on and on, but they pretty much It's what I just said it is. So. Yeah, so here, for example, right, the biological organisms, well, that's very organized things. You just have, for instance, a plant photosynthesis. So you just have, all you have is sunlight coming in, and then photosynthesis happens, and a very complex organism, a plant will grow as a result, but it had to have energy put in for that to happen, right? So it's at the expense of the greater universe that entropy was decreased, right? Entropy increasing means becomes more disordered. So it's just a natural flow of the universe. But if you put energy into the system, and what I say is at the expense of the sun. Well, the sun has photons that have more energy. But once it gets absorbed by the plant, now that energy that was in the photon sun in the sunlight, it's now been put into the plant, and eventually the plant decays, and so that those high energy, the high energy that was in the sun has now been decreased, right? So entropy for the universe has increased. Disorder has increased. And here they're showing that, yeah, see, if molecules inside of a piston, yeah, they're going in all kinds of directions. If you could somehow organize these guys, right? If you could get them organized, instead of just pressure is kind of going in all directions, if you could organize them to all go in the same direction, well, then you would actually have way more force going this way. But it doesn't work that way, right? These things are just bouncing everywhere. You kind of have a general pressure, and then it makes it go this way, right? Because that has like a plunger type thing. But if you could organize them, so they're just going on with that. That seems pretty obvious. Okay, power plants. This is important. Yeah, so let's talk about power plants, right? Why are electric cars more efficient than gasoline-powered cars? Now, because the energy, you have to plug your electric car in overnight and recharge it. So that energy has to be made somewhere. Well, it's off being made at a power plant someplace. The difference with power plants is they run at really high temperatures, 500 or 600 degrees C, really high. And then when they're done, so they make steam, right? So the water boils. They have really high temperature steam. It turns these turbines, right? I think there's a picture. I'm always talking ahead of myself. Yeah, here you go, right? Okay. So say there's a nuclear power plant, right? So what it does is the nuclear power plant, all they do is they just get heat out of it. People are thinking, what? So yeah, it's just like any other power plant. So you just get heat. You have a source of water. The steam is really hot, 500 or 600 degrees. It turns a turbine. So basically, it's just a turbine. You just have the steam that goes through, and it's like a windmill, except it's a long kind of thing, and it spins. This pressure from the steam turns this, and it spins, and then you have a generator, and it makes electricity, right? Now coming out of here, the steam is at a much colder temperature. Instead of 500 or 600 degrees Celsius, it's about 120. So it's just above the boiling point, right? And then, so it's cooler here, and then it condenses back down into water, and the system goes. But the thing is that power plants are efficient because the temperature difference between here and here is very great. It's like 400 degrees. Your car engine isn't that efficient. You don't have those great temperatures. That's why electric cars are more efficient, even though you still have to make the electricity. Even though you ship that electricity over long distances, it's the difference in temperature, so you have a greater efficiency. Ta-da! Now you know that. Yeah, so you got to use some sort of, you have coal, they use coal, they use natural gas. There's lots of sources you can do to heat up the water, right, in these power plants. Yeah, so the steam just runs through the turbine. So the steam goes through and it just turns this thing, right? There's fins in there, so it just turns, and it turns a generator. This is a very basic schematic, right? Of course, it's very much more complicated, but this is generally how it works. And yeah, and then what these are cooling towers, right? So you have that you have that steam. So you have the really hot steam. It does work. Then you have a lower temperature steam, but it's still steam. Well, you want to turn it back into water. So what they do is they run that steam through these cooling towers. That's all these things are. It's not some nuclear radiation thing. At this point, it's just hot water, and it runs through and it cools, and then the steam just condenses back to water. You get droplets that form and the water goes back, and then they pump the water back through the system again. So that's what those things are. Those are just cooling towers. And it's a waste heat, right? So here, sometimes, some places, what they would do is they would be next to a river and they would run the water into the river. It heats up the river and algae grows and all that stuff. So that can be a problem. But here you're heating up the air, so there's always something, right? You never get away scot-free. And here they're just saying, you know, instead of fossil fuels, there's nuclear power, right? Nuclear power is actually pretty efficient. It's just that, of course, there's nuclear waste, and the plants themselves are really complicated because you've got to deal with these nuclear reactions, right? Yeah, you can have geothermal, right? But we don't have geothermal everywhere. You can get sunlight. The problem with the sun is that, of course, it only happens during the day. And then you can only get so much energy, right? The sun only outputs so much energy. You can only get about 800 watts, maybe 600 from a 1 meter by 1 meter square. So it's not very efficient, but it's renewable. The sun is always working, so it's always just giving us this stuff. Of course, if you have a whole bunch of solar panels and you knock down a forest to build solar panels, well, now is that being green? Well, no, that's not being green, right? So you have to. And here they're focusing light to a big tower. One of my first jobs, way back in the 80s when I graduated college, I almost worked on a system like that, but I ended up going into space, which I was happy. So, all right. Yeah, here what they're just saying, if you're able to, you know, when you're able to achieve higher temperatures, that's when you get a lot more work. You're able to do a lot more work when you have higher temperatures, because that steam is really at a high pressure, and you can get a lot of work out of it. If you're at lower temperatures, well, your steam doesn't have that much pressure, so you're not going to get so much work out of it. Yeah, low-grade heat, it might be good, like you could run heat through your house and kind of warm it, but you're not going to turn a turbine if you only have, 100 degrees C. At 500 C, yeah, you'll have a lot of pressure. You can turn a turbine, right? So, perpetual motion. Okay, what this is, there's all kinds of scams. Let me check the camera. I have friends on my Facebook, just friends in general, who are not engineers. They didn't have physics. They're always posting things. Hey, look at this guy. He's got a car that gets 600 miles 600 miles per gallon and all these kind of things, and I'm just like, oh my God, right? And I'm always the bad guy because I have to go, no, that's a scam, it doesn't work, and then they're always going, and then they don't know whether to believe me or not because they don't know anything. So they're like, well, is Felix right? We know he's an engineer, but this YouTube guy looks pretty good too, and they're in no position to make an educated guess, and I'm always in these like situations. Now, you folks and me, well, we know something about this, right? But you're dealing with people who, oh my God. Anyways, yeah, perpetual motion. These are all these scams where they're saying you're getting more work out of the system than you really can. So here's a diagram of a perpetual motion machine where you have this much heat coming into a system, and clearly, so this arrow is fat. They're saying, well, you're getting way more work than you put in, right? I remember when I was young, my cousin, he was talking about a system where they had all these, you would lift a weight, and then when it came down, well, so you're converting potential energy to kinetic energy. He goes, and then when it hit the bottom, he goes, there's enough energy left over that you could lift it again, and there would be excess energy you could use for work. And I told him, no, that won't work. That's impossible. You can never get more work out of a system than you put in. Plus, there's friction, pulleys and stuff. There's always friction, even if you oil everything, right? That's a perpetual motion machine. I told him that too. I was really young, and I was an engineering student. And I said, that's a perpetual motion machine, right? So I knew enough to say that. So if someone's showing you some scam, just you can look at it pretty simple. Just think, well, how much energy are they putting in? How much energy are they getting out? If they claim they're getting more energy out than you put in, that's impossible. That's perpetual motion. You can point at them like I did when I was a young person in college and go, no, that's a perpetual motion machine. And he's my older cousin too, right? So, but I told him. Yeah, they talk about first kind and second kind. We're not going to worry about that. We're just going to worry about any kind. Any kind of system where you're getting more work than you put in, that's perpetual motion. We're not going to worry about first kind and second kind. We're going to worry about any kind, right? Yeah, so here's a diagram saying that all of your heat is going into work. Well, we know that's impossible. You're always going to have waste heat. Always, 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 right? Heat, if you have something heated, it's going to go into the metal. It's going to go into it's going to leak into the metal, and then on the other side of the metal, it's going to leak into the air. You're always going to lose heat. It's always going to have inefficiencies, right? Yeah, here's another thing they're saying. They're saying that they're just kind of giving you a little test here. So the theory is that this is really low. So this water. So since this water is so high, it should have pressure that would force this, and then they said, would it go up here and turn a turbine? No. What would happen is that this water would go as high so that it's equal with this pond or lake, and then it would stop there. The water would never go higher unless you did some kind of work. What would happen in a natural system is that this pipe would go, and the water would naturally just stay right here. Right, and the air pressure would be here, same air pressure that's on there. It would be right here. In order to get the water higher, you would have to put work into the system. You're not going to get work out of a system like this. That's all they're saying. All right, here they're just saying, yeah, you can't do that. You got to have some waste heat. There's always waste heat, right? So that's all they're saying. Perpetual motion machines. This is important. This is the sort of thing. The internet is full of all this nonsense. You folks are now armed. You now have the defenses where you know, like, okay, here they're getting more work out of the system, right? So you keep, right, because this line is bigger than this line. You can never get more work out of the system than you put in, right? These things are easy to spot. Here's another one, some crazy thing where they're putting the heat back into the system. No, and the work went that way. Okay, that's not right. So these are just examples. Here, naturally, will a system ever flow from a colder to a hotter? No, that will never happen. Heat always flows from hotter to colder. It never goes from colder to hotter unless you do work. Like for a refrigerator, you keep the inside of the refrigerator cold, but you have a pump where you're expanding gas, right? And that makes a colder temperature. So you have to do a lot of work in order to keep inside of the refrigerator cold, right? So they're just giving examples. This is important, right? You people are educated. You can go out there, you can see these crazy internet videos, and your friends are talking, oh, why don't they just make cars? I saw on the internet where cars get, 300 miles per gallon, and you can tell them, no, because, right? So, all right, so this is, oh my God. Yeah, so here they're saying it's okay because you're doing work, right? This is like a refrigerator. So the diagram is correct. More heat is transferred to the hot reservoir than is taken with work being done. So this is a refrigerator, right? So you have the refrigerator motor is doing work on the gases, right? It's expanding gases and compressing gases, and it does all this work. Then you can have a system like this, right? But we know that. And that's it, folks. That's it. That's it for that chapter. So let me just check my notes quickly. Okay, that's it, folks. Be safe.